teachers.
For sure.
You know exactly what you're doing, but you're not communicating it.
I've met some real doozies at the U.
Yeah. Okay, so anybody have any homework questions before I get into new stuff?
Oh, 2D.
Okay.
I thought I got it.
Where? This is, I don't have these numbered, so this is incompressible and ideal gas.
Mm-hmm. You said use first law. I'm like, does that mean I have to calculate work? No.
Okay.
Spiral. D.
Oh, that's the one you want, D?
What else?
Details.
Yeah,
There's no D.
there's on mine.
Oh, I wonder if,
Number 3D.
oh, 3D.
No, on mine it's 2D. On yours it's 3D. What is the heat Q added to water?
Oh man, I gave you guys I gave you an earlier set. That sucks. You only have 8 questions. I better make sure that doesn't happen anymore. Okay. So, okay. So let's see. Is that 3 on this one? Okay, that whole thing is my number 3 and your number 2.
Well, they just got misnumbered.
I think
Some.
yours is an older set. This is a newer set. Okay. So it's liquid water. We know it's incompressible. And so one of the big things we know is that if we have the specific heat, we can calculate changes in specific internal energy as C times a difference in temperatures. The specific heat for liquid water, well, let me show you where to find that, because we just talked about this yesterday in office hours. Click, 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 click. And in only 8 clicks, you're into D2L. Okay, so here's where to find the specific heat of incompressible materials, and water is one of them. Go to tables, go to complete property tables, and then properties of common liquids, solids, and foods. We will not do any foods in this class. Well,
It's not a part of thermodynamics.
I guess it is, but we're not doing it. Okay, so you can see that over on in the right column, it tells you the specific heats. And let's see, water. And it tells you what it is for a few different temperatures. So you can find the one that's most applicable to your temperature range. So you can see it doesn't vary that much percentage-wise from 422 to 418. But we have it at 100 degrees Celsius, so we want it to be exactly 4.22. And the units are kilojoules, so I'm going to call that 4220. Okay, so C is 4.22 times 10 to the third in SI units. So that's part A. Part B, okay, so now we're going to figure out the temperature at saturation. The pressure is 2.1 bar. And so now I'm going to go to, it's just a little more convenient to go to the tables that are just water for this. And we want to look up temperature by pressure, indexed by pressure, and we want it at saturation. And we want 2.1 bar. Well, we have a 2 and a 2.5. So let's see, 120.2, 127.4. I don't know if I can remember that. So the temperature that we want, we can approximate it as 120.2. So 120.2 plus 127.4 minus 120.2 divided by 2.5 minus 2 times 2.1 minus 2. And so that is 7.2. What did you get?
121.6.
Okay, yes, that's what I get too. 121.64 degrees Celsius. And you can see, at atmospheric pressure, the temperature of saturated water, whether it's a saturated liquid or a saturated gas, is 100 Celsius. So this is a little higher as the pressure goes up. Intuitively, it's because as you apply more pressure, it's harder for molecules to escape the surface of the water. And now we're going to use the incompressibility assumption to calculate the changes in H. Change in H. Okay, well, let's see. The change in H is the later H minus later H minus the earlier H. And we can write that as U2 plus P2 V2 minus U1 plus P1 V1. And now we can rearrange this as U2 minus U1 plus P2 V2 minus P1 V1. And now you can just think of this as the change in specific internal energy plus the change in PV. Okay, so this is what we're trying to calculate. And putting it in this form, then it's clear that you can calculate the change in U as 4.22 times 10 to the third, the specific heat, times the change in temperature, which is 121.64 minus 100. And so the change in specific internal energy is 91,320.8 joules per kilogram. And now for the change in PV, you can think of the definition of an incompressible material being that the specific volume doesn't change or the density doesn't change. So you can rewrite this as the V that's constant for the whole thing times the change in pressure. And we have a constant pressure, so this is just going to be 0. And so the change in specific enthalpy is 91,320.8. It asks for the change in the extensive enthalpy. And so that's just the mass times the change in specific enthalpy. We have 10 kilograms. So this is 913,208 joules. So we made this jump because it's incompressible. Okay, what's the Q added to the water during this process? We're assuming that this is incompressible. And so the volume is constant. Okay, so the work for an incompressible material is this, but dV is equal to 0. So there's just no work of expansion for an incompressible material. There's no way you can have work of expansion. And it doesn't mention any other types of work, you know, electricity coming in or going out, rotating shafts. And so the work is equal to 0. So now we can say the change in internal energy is equal to Q minus W. W is 0. Now, change in enthalpy is definitely not always the same as the change in internal energy, but in this case, since we have no change in pressure or volume, we got that they're the same, and so this is equal to, I mean, really, let's just go from here. So the change in extensive internal energy is 913.208 913,208. And so we have 913,208 is equal, this is joules, is equal to Q.
Damn it. Okay. Yeah, the incompressible W shouldn't have.
Okay.
Cool. Thank you.
Yeah. Any other homework problems you'd like to see? Volume analysis. And we're using two equations with control volume analysis. The first one is the mass balance. And we're done talking about that. The second one is the first law. And so now I want to go through the derivation of the first law for control volumes. And I want you to notice, I mentioned this once before, like what is enthalpy? Sometimes you hear people talk about an intuitive meaning for enthalpy, but I think really just think of it as like kind of a mathematical artifact. It's just something that pops up in calculations. And I want you to notice that enthalpy pops up in this derivation. And so with control volumes, deriving the first law of thermodynamics, you can think of this as the device. So this is the control volume. We're looking at this. And material is always coming in. And material is always going out. And we have to account for changes in properties due to this stuff coming in and out. And so the first law, we're going to start with this kind of basic idea. The time derivative of the energy in the control volume is equal to the rate of heat transfer into the control volume minus the rate of energy out of the control volume. Plus the energy carried into the control volume by material minus the energy carried out of the control volume by material plus the work done on the control volume by pressure at the inlet minus, let's see how, work done. Let me just make that a plus. So let's word it the same way. So plus work done on the control volume by pressure at the exit. Okay, and all we have to do now is come up with, mathematically derive these four terms that we don't know what to do with. So the first one is energy carried in at the inlet. And all of these are rates. And so anything that I use a subscript I for is going to be at the inlet. Anything I use a subscript E for is going to be at the exit. And so what's the energy being carried in at the inlet? Well, just take all of the energy terms. And so it's going to be 1/2 times m dot times the speed squared at the inlet. This m also should have an inlet. That's the kinetic energy coming in. Plus the potential energy, the rate of potential energy coming in. So that's m dot I times g times, we'll call it zi for the height. That's just gravitational potential energy.
That's V.
That's V, yeah, but since I'm calling this speed V, I'm going to leave the V out of it. So make sure that you're thinking of this as speed. And then plus mi dot ui.
That's little u.
Right. Yeah, that's why. So all of these are little. That's why we're multiplying by the m dot.
Sure. So that would be actually a little.
Well, that V isn't the property.
Well, I meant the T, but no, it would be the big T because it's
Yeah.
total.
That's just the definition of kinetic energy is 1/2 mass times speed squared. So that's the only one that's different.
Like the unit values.
Yes.
The total values.
That's
separate in my head.
Yes, that's like the whole game, I guess. And then the energy carried out at the exit, well, it's going to look exactly the same. So that's going to be 1/2 m dot at the exit times the speed at the exit squared plus mi dot times g times the height at the exit. This shouldn't be a I, this should be an E. Plus m dot at the exit UE.
What was Z again? Sorry.
Z is just the height.
Okay.
Yeah. But I don't want to use H because we're going to use that for enthalpy eventually. All this could be avoided if we had more letters in our alphabet.
Let's just go shapes.
I wonder if this is easier in Japanese.
Seems unlikely, but
Like they have more symbols though.
Yeah. Okay, so now we're on to the two that are gonna, we're gonna have to think a little bit more about these two. That's the work done on the control volume at the inlet and the exit. So the work done on the control volume at the inlet first. And these are all rates. So work, remember, is like force times distance. Let's think of it as force times x. Okay. And this is if F and X are in the same direction. Okay. So the rate of work is just the time derivative of this. And you can write that as, if we assume that this force isn't fluctuating in time, this is equal to F dx dt, which is equal to F times the speed.
That'd be W dot.
Yeah, although I want to be careful about, because we're using kind of this thing's own sign convention. So I don't think I'm going to use that W, because we're used to W being positive if energy is leaving the system. This is energy coming into the system. And so now how are we going to express these two things? Well, I said that this force is caused by the pressure, okay? And we want the pressure that the surroundings are applying to the control volume. So force is from pressure, and the pressure of the surroundings is applying a force in the same direction as the fluid flow. So we can rewrite this as, the rate of work is equal to the pressure times the area times the speed. And then finally, we can rewrite the speed in terms of properties we can look up using, we know that m dot is equal to a times the speed divided by v, the specific volume. And so we can rewrite this, calculate v is equal to m dot v over a. And so our rate of work here coming in at the inlet is P A m dot v over a. The a's cancel, and we get m dot p v. And this is at the inlet. So let's put inlets on all of these. So m dot at the inlet, pressure at the inlet, specific volume at the inlet. So that's all stuff we can look up in the table now in place of all this stuff that we couldn't look up, just the force and the speed and stuff like that. And now we have to do this one more time at the exit. So this is the work coming in to the control volume due to pressure, the surroundings, apply to the control volume.
You say pressure from the surroundings, would that be like a pipe or something?
Well, okay, so look at this picture. So what this is saying is there's a pressure right outside this door at the inlet, and that pressure is applying a force, and that force is doing work on the stuff that's in the control volume. And over here, there is a pressure right outside this door this time it's pushing back this way. And so we're going to have to deal with the fact that that pressure is in the opposite direction of the fluid flow here. That's going to change the sign, but that's the idea.
But does it have to be? I mean, could there be like a low pressure pulling the fluid out?
There's no, pressure never, when you're thinking of absolute pressure, so when you think of stuff in terms of gauge pressures, you can get negative pressures and suction and stuff. But when you're thinking of absolute pressures, all pressure does is push. It's just a matter of which side is pushing harder, And so the pressure out here is pushing back that way. There's nothing it can do. Even if it's close to zero pressure, it's still pushing a little bit back that way.
Okay.
Yeah.
Yeah, atmospheric pressure.
Well, it doesn't have to be the atmosphere. These could be pipes coming in or whatever. Those pressures could be really high. The way I have it drawn, I guess it sort of looks like it's atmospheric pressure, but we'll see, really high pressures for those too.
But yeah, so you're just, in this case, you're looking at them individually.
Yeah. Right.
And then, it doesn't really matter.
Right.
Because you're just taking this side and then this side.
Yeah, exactly.
Whatever the result is the result.
Right. So let's see. Work done at C. Okay, so I was a little more wordy here, but this is the same as number 3. Okay. The difference is at the exit, the pressure and the fluid flow are in opposite directions. Okay. So the rate of work in this time is equal to negative. That negative comes from the opposite directions thing. Force times speed. And then we can replace the force with the pressure times the area. And then we can replace the speed keep that negative sign there. M dot, again, is equal to AV over specific volume. And we can use that to calculate the speed. And so our final rate of work in to the control volume at the exit is negative P A M dot V over A, and that's negative M exit dot times P exit specific volume exit, and that's it.
Are they always inverses or opposites?
They always have opposite signs. Yes, they always have opposite signs because pressure is always against the flow at the exit, and it's always with the flow at the inlet. And so now we can put this all together. And we have that dE dt in the control volume is equal to Q dot, heat flowing into the control volume, minus W dot, that's the work done by the control volume on the surroundings. And now we're going to get into the other stuff. So we have plus all of this. So let's go 1/2 m dot v I squared and put an inlet on that m. Plus, question? What? Are they? I don't know. I'm too busy trying to keep my variables straight.
Sorry.
And mi dot gzi plus mi dot ui and now I'll do the one for the exit. So plus, and this one, so now this is energy carried out. So I'm just going to subtract this right from the start. And in parentheses, it's 1/2 m dot exit times speed at the exit squared plus m exit dot g z exit plus m exit dot u exit and now we're going to the work at the inlet. So plus m inlet dot pressure at the inlet, specific volume at the inlet, minus m dot at the exit, pressure at the exit, v exit. And we can make this look a little nicer. So I'll simplify this a little. So we have dE dt at the control volume is equal to Q dot CV minus W dot CV. And now I'm going to group all of the inlet stuff together. So plus M inlet dot times the quantity 1/2 V inlet squared plus M, no, I already pulled out the MIs. So plus G Z inlet plus U inlet plus P inlet specific volume inlet. And then we're going to subtract all the stuff at the exit. So minus ME dot times the quantity. And then it's going to be all this same stuff again, but with exits instead of inlets. So 1/2 V exit squared plus GZ exit plus U exit plus P exit specific volume exit. And now you see where this enthalpy comes from. This is the specific enthalpy at the inlet, and this is the specific enthalpy at the exit. And so I'm going to rewrite it one more time in the form that we're going to use. So dE dt for the control volume is equal to QCV dot minus WCV dot plus M inlet dot times the quantity. I'm going to write this, just going to rearrange it. So inside the parentheses, HI plus 1/2 VI squared plus GZI, and then minus ME dot times the quantity H exit plus 1/2 V exit squared plus GZ exit. So there it is. That's the full form of the first law for control volumes. And I think probably in every single case, definitely in most cases, so let's say almost always, we'll start from this full form. And then simplify it according to the specific problem.
Like a lot of that stuff just end up as 0. Or...
A lot of it will end up 0. Yeah, that's right. And I think I'm not going to start this list. Let's just start there. But on Friday, so I'll go through the list of things to look for that are going to let you cancel terms. In most cases, we're going to end up with just, 3 or 4 terms left. It'll simplify a lot. And then after I talk about the ways to simplify stuff as kind of an example, I'm going to go through these 5 specific devices that are going to come up from time to time. So, any questions right now? Okay. So if anyone asks you what enthalpy is, just go through this derivation. Like, to me, that's,
Just list it off.
yeah, that's all enthalpy is just a mathematical simplification of a bunch of stuff that popped out of this derivation,
And that's why enthalpy changes on those tables, because it depends on P and V.
Yeah.
Right? Or I guess that's the V is that's specific volume.
Yeah, that's specific volume. Yep.
Kind of like an outward pressure, like a surface area type pressure kind of.
You can think of like what's enthalpy. Enthalpy, if you want to think about it, you can think of it as the work that's required to make space for your substance plus the internal energy of that substance. So it's like not just the internal energy of the stuff, but how much you have to fight to make room for it also. So to go from that stuff not existing to the energy of it existing kind of in its space. I think that's sort of a way you can think about it.
And that's why the pressure is opposite of that outlet. It's having to make space.
That's not, that definition of enthalpy is not why. I think that just think of that negative as coming from the fact that, like, when you think of the definition of work, I mean, we were putting in the rate of work of being done by the outside pressure onto the control volume. Okay. And work, remember, if the force is in the same direction as the motion, work is positive. And if the force is opposite the direction of the motion, work is negative, like slowing something down, you know? And so since the pressure always at the inlet acts in the direction of motion, it's always positive work on the system. And since pressure is always opposite the direction of motion at the exit, it's always negative.
That makes sense.
Okay. Any other questions? Okay, that's all.